Well, good afternoon, everyone. I can't tell you how pleased I am to see such a wonderful gathering here, and I've been so excited about this session, P-values and statistical significance, their impact on research today, which has been organized by the Johns Hopkins biostatistician community, an entity jointly sponsored by the Department of Biostatistics here in Public Health, as well as the Johns Hopkins Institute for Clinical and Translational Research. So my main task really is to welcome you. Again, it's just great to see so many people here, as well as to provide some thanks. And so in a minute, I'm going to describe a little bit about the community, just so that you know about it for those who don't yet. The community has 4 working groups, and so one of them is the professional experience work group, and so that work group is responsible for organizing this fantastic session, led by Jamie Perrin and joined by Jiangsha Wang, Yulia Sava, and Carol Thompson. And so it's just, I'm amazed at the event that you put together. I'd also like to thank Nita James, who did all of the organization and got these lovely lunches together for us and all of that. And then finally to our speakers, which I was incredibly delighted. We sort of brainstormed, and the group said, oh, why don't we ask thus and such and thus and such, and people that in some cases we really didn't think that we would be able to get, and they all said yes. And so you're really going to have a wonderful session. Let's thank all of these folks. So just a little bit about the biostatistician community, and I'll just narrate a little bit how it arose. Those of you here, I guess all of us are here from Johns Hopkins, know that we have a very organic place. It's a ground-up place. We have 2 departments of statistics or biostatistics, as well as a major division of biostatistics. We also have a department of epidemiology, but there are many, many biostatisticians, statisticians, epidemiologists who don't live in any of those groups, So we have this widespread community, which is wonderful for the institution, but I think can be isolating for some people, and we do tend to get siloed, and for sure there's people in this room that I should know and I don't know very well or maybe at all. And so it just seemed that we needed to address that a bit. And so we set out to create a connection between hopefully all, but at least as many of the statisticians, biostatisticians, epidemiologists at Johns Hopkins who are engaged in applied research and have begun to call that the Johns Hopkins research community. And so, breaking down silos is one mission. Enhancing the professional environment by sharing best practices is another mission. And just really creating a community where people get to know each other and can form friendships that enrich, the whole of our lives and not just our professional lives. And so there's approximately 180 quantitative scientists on the listserv. That is fantastic. And I've already alluded to work groups. We formed 4 of them, and I'll briefly describe them now. So the first one is advocacy, and that one has been led by Larry Moulton as well as others. And so its purpose is to advocate for clear career paths and opportunities for career development. So in as heterogeneous an environment as we have, these sorts of things can vary widely. And we'd at least like to share information and try to optimize those to the extent that we can. Each group has an initial focus. This group is focusing just on identifying the various career paths and making comparisons across quantitative specialist positions across the Johns Hopkins research community. We have a best practices work group, which is being co-led by Chen-Li Xu and Josh Betts. And so, as you can see, it aims to promote sharing of resources and best practices so that together we can be providing the highest quality quantitative support as we can. And so its initial focus is to develop educational online things, and so a blog to share statistical approaches, case study examples, newest techniques, and I can tell you that that effort, at least I've seen a piece of it begun to be piloted in the Center on Aging and Health, and so I'm very, very excited about that. We have a networking work group is being led by Kit Carson in the Welch Center, and so it aims to provide networking opportunities for all of us. There was a luncheon held in June. Even before that, I guess there was a inaugural event held in the previous September, and I was really amazed by how many people came, you know, to the one that I was able to attend, just really indicating the energy that exists. There's some social media activities going on, so a Facebook page at least, which is called Be More Statistical. I understand that a Twitter feed is under development, and so, you know, keep your eyes and ears open. Anyone can access at least the Facebook page and then request permission to join, et cetera. And big plans maybe to expand to University of Maryland and other Baltimore entities, perhaps even reaching to a chapter, you know, which has proved to be a really valuable experience for many of us. And then that brings us finally to this work group, which will aim to host intellectual enrichment events like today's, as well as other professional experience, and just to be a resource for opportunities. And so I couldn't imagine a better kickoff than we have today, addressing a hot topic, the current status of p-values in research. And so without anything more from me, I would just love to get the event started. And to do that, I'm going to pass off to the leader of the work group, Jamie Perrin. Thank you.
Thank you. Thank you, Karen. Thank you and welcome. We're very pleased to have 4 distinguished panelists here today to discuss the status of p-values as they impact the research we support as biostatisticians, epidemiologists, and data analysts. For our inaugural event, we wanted to bring the community together around a topic that would have a broad base of interest because we practice in so many different application areas. P-values and statistical significance have been the focus of some highly visible discussions over the last few years, including a ban of p-values from several journals, discussions around the reproducibility of scientific conclusions, and a statement on p-values released earlier this year by the American Statistical Association, including a session at the joint statistical meetings. As quantitative scientists, we have a responsibility to foster understanding and the best use of statistical significance by our collaborators, our students, in addition to the public. So that's what we're here to talk about today. So I'll go ahead and introduce our panelists. Each will have 12 minutes to speak, and a question and answer period will follow after they have all presented. So they will speak from right to left, and in that order, they are Dr. Jeff Leek, Associate Professor of Biostatistics here at Johns Hopkins, Dr. Gary Rosner, Professor of Oncology and Biostatistics, also at Johns Hopkins, Dr. Moises Sklo, Professor of Epidemiology and editor-in-chief at the American Journal of Epidemiology. And finally, we have Dr. Ron Wasserstein, executive director of the American Statistical Association, and a co-author of the statement on p-values released by the ASA earlier this year. So our first speaker will be Dr. Jeff Leek, and the title of his presentation is "The P-Value Really the Problem?"
Oops. Let's see if we can. See if that worked. Okay, yep. So I'm Jeff, and I will serve as your p-value apologist for this particular discussion. So I'm going to lead off in the pro, and we'll be followed by the con, I imagine, at some point. My argument or my discussion today is about whether the p-value is really the problem we should be thinking about or focusing on as statisticians. So p-values have been a focus of a lot of debate for a long time. The most recent iteration of this was when a psychology journal, I think to some extent because they believed it and to some extent because they wanted press, banned p-values from their journal. This is a relatively well-respected but not one of the top psychology journals in the world, and so this is a great way to get yourself into Nature, is to ban p-values. And so there was a long discussion that this engendered, kind of concluding with the ASA's statement, I think concluding with the ASA statement on p-values, and I'll let Ron talk about that. It was an outstanding sort of summarization of the issues with respect to p-values, and I think everyone should read it. It's really well done. And it sort of spilled over. P-values is one of those things that everyone is aware of on some level in science, but it's amazing that it was also sort of popular sites like 538 and others picked up on this p-value ban and the discussion about p-values. So like I said, I'm going to be the apologist. So I think p-values and hypothesis testing get a bad rap. And so this is a post I wrote with a colleague, Rafa Irizarry, about p-values and why we think they're okay. And one line I thought I'd highlight is that if he was cited every time a p-value was reported, his paper would have, at the very least, 3 million citations, referring to R.A. Fisher's paper on p-values that doesn't exist, but if it did exist, would be the most cited paper in history. So this is about an order of magnitude higher than any other paper that's ever been written. It is the greatest hit of statistics. It is by far the most widely used statistic. And so I think a lot of my argument is going to be a p-value is suffering a lot from its success, and it's maybe not the p-value that is to blame. So this is my argument for why people don't like p-values, courtesy of Taylor Swift. It's for you, Martin. I know you like Taylor Swift. So I'm going to talk about 3 main arguments here. One, I think the reasons why there's trouble with statistics right now is not because of p-values. It's for these 3 reasons. Statistics is often an afterthought. There's something called research or degrees of freedom that we allow, that we haven't studied very well, and we think of each individual study as like the end of the discussion about a particular scientific problem. So we'll start with the first. Statistics is an afterthought. This is my son Hank after you pull him out of the pool. He hates it, and I think a lot of people feel that way about statistics. I know that that's true because this is, no joke, a published paper, the abstract, and you'll read in the abstract, insert statistical method here. That was a little embarrassing, but not that embarrassing because nobody likes statistics in the first place, so that's probably why it got past peer review. And then this is another one. This is from a supplemental material. Emma, please insert NMR data here. Where are they? And for this compound, just make up an elemental analysis. This is a paper that launched 1,000 blog posts in the chemistry literature about whether they were being nefarious or not. I don't think they were. I think they just, like everyone, statistics is the afterthought. And I think to some extent that's the source of our problem, that we care about statistics a lot as a community, but it's not necessarily something scientists care about until the very end and only kind of like as a toss-off. And that's why there are these problems, I think. To prove that one more time is, these are the medical school entrance requirements. These are the courses you have to take. There's no statistics on here, and it's stunning. Every single paper in the New England Journal of Medicine has a statistical argument in it or a statistical model in it. Every single statement we make about medicine is in some way backed up by data and statistics, and yet we don't need doctors to know about statistics, apparently, which is, I think that's the source of the problem, is that we're not teaching everyone about statistics, even though everyone needs to know about statistics. My colleague Rafa wrote a post about this in my field, genomics, where he says people in positions of power that don't understand statistics are a big problem for genomics. And I think that that's true. I think that a lot of the senior leadership, scientific leadership in a lot of fields have treated statistics as something that they have to get past or get around or do at the very end, rather than as a central component of what the science that they're doing. And that leads to something that I think is very important to this community and why I'm so excited about this biostatistics support community. In my field, it's called the lonely bioinformatician. It's the one bioinformatics or biostatistics person in a biology lab that's like responsible for all of their data analysis and has no connection to the broader community. And that is a struggle for a lot of people. And I think without empowering those people to have, feel like they can contribute to the scientific process, we'll have a lot of trouble. The second one is researcher degrees of freedom. So I think the first thing is statistics is an afterthought. The second thing is researcher degrees of freedom. So when we teach statistics, it's often like this. Y is some outcome, X is some covariate, Y is a continuous value, so you fit an LM and get a p-value and report it. And the problem here is not the p-value, right? The problem is that we teach statistics like this, and in reality, there's extreme scrutiny about the p-value at the end of the data pipeline, and then nobody cares about any of the stuff that happens before that, right? Like there's no discussion about how do we summarize the data, how do we do experimental design, and so forth. This is a sort of a zoomed out view of that process. LM is just down in the modeling component. This is a slide from Hadley Wickham who's talking about the entire data analysis process where you import data, tidy it up, transform it, visualize it, model it, and then communicate it. And how did I learn, so you might want to ask yourself some questions about this process. So when and where to do it is wherever Ingo Rosinski is working right now. That's where you should be doing data science. This is a picture from Courtesy Ingo. And then how you should do it, these are the ways that I import data, say with the Google Sheets package, and I use the Lasso for modeling maybe, because that's a shout out to Ciprian Crenicianu. And then I visualize data with base R packages and I communicate them with PowerPoint presentations. What are the reasons I use these? Well, maybe bad life choices for my visualization techniques, because I like sparsity for modeling maybe, because some person told me that's a good package to model my data with that way, and because PowerPoint owns everything, so that's why I do communication that way. None of these are scientific reasons why I do any of these things. It's sort of just culturally what I learned or whatever was laying around. And so in general, we don't have a systematic way of measuring and describing why we do certain things and which ones are good and which ones are bad. We call this, my colleague Roger Peng and I call this data science as a science. We need to understand the ways and reasons why we do data science. An example of that is, this was sort of pointed out, p-hacking is a way to like put down the p-value. Oh, you can fiddle with parameters and get whatever p-value you want and report it. And my read of that was not that the p-value is stupid, it's that there are like a million choices that you can make and we don't know why you should make one or the other, right? So the problem isn't that there's a number that comes out at the end. The problem is that we don't understand why you do one of these 400 different choices. And so I think that the researcher degrees of freedom is something that's really poorly studied and needs to be studied. And so as a component of that, me and some of my colleagues teach these massive online open classes. So we have taught something like 4 million people over the last 2.5 years. And so we've created the most dangerous set of early trained data analysts in the world. And so something we worry about is scalability, right? You teach people something, you're going to teach it to a lot of people. How scalable is that? And in terms of a statistical procedure, sure, the p-value has got problems and it's hard to interpret and everything like that. But the reason why we talk so much about it is because everyone is using it. Thank you. And so I think that any other sort of technique would suffer from the same consequences once it went to that many people. So that was the second thing. And the third thing is the study as the unit. So when asked why people think there's so much reproducible research, scientists reported the two top things are selective reporting and pressure to publish. And those are both career reasons. They're not statistics or the p-value or interpretation of statistics. It's because they're being sort of pushed to report results, positive results in a certain way, and they feel like they can't avoid that. And so I think that we should have a discussion, if we're going to discuss why there's this problem in science, it has to on some level go back to what are the factors contributing to why people do this. So this is a blog post written by Roger Peng, and he talks about a simple explanation for why we're having this statistics or replication crisis in science. And it's not the p-value, it's that he says that the replication crisis is largely attributable to a mismatch between our expectations of how often findings should replicate and how difficult it is to actually discover true findings in certain fields. And what he means by that is when we publish a single study that shows a significant result, currently we think of that as a gold standard, like there is a study that exists that reports this result. But there's error and variability in that. And so the less credibility we give to any one in particular study, the less pressure there'll be to publish one particular type of study. And the more we think of it as this is just one piece in a puzzle about building up knowledge about a particular area of science, the less likely we'll find ourselves in crisis scenarios. I think it's a great blog post. So the reason why I think that this is a problem for people is right now, the pressure makes it seem like this. It seems like on the one hand, you get a p-value, gold, and on the other, painful, agonizing failure, right? Like either your p-value is less than 0.05 and you get success, or it's greater than 0.05 and you don't get success. And so I think that's attributable to this idea that one study is the gold standard for why this scientific result is true or false. And the more that we can do to tamp down that belief, the less that this is what the perception of any particular scientific study is, and the less pressure there'll be on people to chase a particular level of statistical significance, regardless of what they use. So I think it was Winston Churchill that once said, "Indeed, it has been said that p-values are the worst measure of statistical significance, except all the other forms that have been tried from time to time." And so I might have varied that a little bit. And but I think that this is true, that regardless of what procedure we use, there's still this pressure. People are still going to game the system. If we choose a Bayes factor or a likelihood ratio or whatever you pick, people will find a way to game that to get their publication if the system is designed that they only get their grant if they get the publication, which requires the Bayes factor to be X, right? So I don't think it's the p-value so much as the culture of science that is the problem for statistics right now. The reason why we're at the heart of it is statistics is fundamental to every single discipline, so it's a unifying principle that people think of us as the gatekeepers. And the more that we can sort of tamp down that belief that like any one paper is the result, the better off we'll be. So anyway, that's my presentation. I think this is the real issue that we have rather than p-values, and I think p-values work fine as one of any number of measures of significance we could have picked to use. They will have problems just like any other procedure that if you scaled it up to 3 million people citing it would also have those problems. And that's the end of my presentation. Thank you. Are there questions or is it?
Okay. Thank you. Oops, is that not working?
Hey, Jeff, great talk. No, thank you very much. It's nice to understand the top statistician for the change.
Thank you. Next, we'll have Dr. Gary Rosner. To P or not to P, is that the question?
Okay. Thanks. Excuse me. How do you get to full screen on this? Get rid of the other stuff? Was it Control L or something? I should have used Jeff's computer, because I know that one. All right. Thanks for inviting me here. I think this notion of bringing together all the individuals at least on the East Baltimore campus, if not through the rest of the university, who are working on statistics or applying statistics in different areas, I think it's a wonderful, wonderful idea. And I hope that we can do more of these things. All right, I only have 12 minutes, and I've already used up probably about 3 of them. Anyway, so this is based to some extent on a talk that I gave with Karen. We were on a panel, sort of, at the East North American Region's annual meeting in March of 2015. That was a late-breaking session because of the announcement by the psychology journal that they were going to ban hypothesis testing. So, assuming that I may well run out of time, my main points, I'll tell you right now. I think journals and also researchers wishing to publish in these journals rely too heavily on hypothesis tests and p-values. And I think, again, echoing something that Jeff had said, reliance on significant p-values leads to irreproducible research. I think journals are somewhat inconsistent with respect to how they require people or how they enforce the presentation of data and statistical results. And I think a particularly insidious problem that I and my colleagues face all the time is the receipt of data from investigators where it's been pre-processed or they've carried out initial analyses. And we don't know what those analyses led them to decide in terms of what they were going to give us, in terms of what questions they wanted to ask of the data. And this is a form of multiplicity for which we cannot easily adjust. All right, I could sit down now, but I won't. So going back to a little history, there was a project, I don't see Tom here. Tom Lewis was part of it when back in the 1980s, when some of us were in graduate school. There was a project that Fred Mosteller was leading with John Baylor. It was the New England Journal Project, and they established some guidelines for statistical reporting articles in medical journals. And many of the suggestions that they made have been made repeatedly, are made repeatedly in instructions to authors from journals, and are not enforced. So in particular, give the details of the statistical methods to the extent that somebody who's knowledgeable about statistics, if given the original data, they could reproduce the results. When possible, quantify findings. Now, I wouldn't say when possible, I would say always. But also include appropriate indicators of error or uncertainty, and avoid sole reliance on statistical hypothesis testing. They also said to avoid non-technical use of technical terms in statistics, such as random or significant. But in particular, what I highlighted was the outcome of a formal test of a statistical hypothesis or test of significance is how it's used in statistics, but significant means that the outcome of such a test fell outside a chosen predetermined region, but it's different from significance in the medical or social sense. And large sample sizes, for example, as we know, may well show statistical significance in situations where the difference is really not at all meaningful. The New England Journal then also has instructions for authors where they say investigators should use tests that control type 1 error, and I'll talk a little bit more about that aspect of it because it relates to, I think, some confusion between Neyman Pearson hypothesis testing and significance testing of Fisher. And they want you to use two-sided p-values. There's this thing that two-sided p-values are always the way to go, even if you're really only interested in one-sided. That's repeated again in several other journals. Also, the Journal of the American Medical Association says that you should include the absolute numbers and measures of risk along with confidence intervals or p-values. So one or the other. And the Journal of the National Cancer Institute says that a p-value or a confidence interval should be cited in the abstract and in the text for any statistically significant finding reported. That means that if you did analyses and they were not significant, you don't have to say what the p-value was or anything, or what the estimate was, or any measures of uncertainty. And outcome variables should generally be given as point estimates with confidence intervals rather than standard deviations or standard errors, which is putting emphasis on Neyman's confidence intervals, which is really just an inversion of hypothesis tests, as opposed to a true measure of uncertainty. Journal of Clinical Oncology has an interesting thing in their instructions to the author. They say if the trial design was Bayesian or used one-sided p-values or was not based on standard two-sided test, you got to give us the two-sided p-value anyway. So what is it that I think authors want when they provide a p-value? And I think authors think that they're giving a measure of truthiness. So some of the history, Fisher was the one who came up with this notion of significance in terms of assuming that you have a model, that the model's correct, and you want to make some assumption about, say, no treatment difference or whatever. How kind of extreme is what you observed given those assumptions? And so it was really just meant to be a measure of discrepancy as opposed to Neiman and Pearson, where they were saying, oh, and it's a measure of discrepancy for this specific study. Neiman and Pearson said, well, no test based on the theory of probability can itself provide any valuable evidence of the truth or falsehood of that hypothesis. Okay, so instead they said, can we come up with a procedure that will guarantee or ensure that we don't make mistakes too often in our careers? And that led to hypothesis testing and type 1 error and type 2 error. So this is really over the long haul as opposed to a measure for a specific analysis. And the two have gotten confused, I think, in a lot of ways. So this, Steve Goodman wrote a couple of papers about p-values and Bayes factors in the Annals of Internal Medicine. They're very, very much worth reading, as is just about anything Steve writes. And he said that basically the hypothesis test, he points out this conflict between these two. The hypothesis test approach offered scientists a seemingly automatic way to limit the number of mistaken conclusions in the long run, but only by abandoning the ability to measure evidence and assess truth in this particular experiment. So it controls error rates overall, whereas the p-values seem to be a measure of evidence of a single experiment that did not violate some sort of long-run logic of the hypothesis test. So it's often used to provide two things that are in conflict, a measure of evidence against the null hypothesis in this study and a means to control overall type 1 error regarding rejection of the null hypothesis in the long run. But you can't have a single number that'll do both. So some examples are multiple comparisons. So we would adjust a p-value because we want to protect type 1 error. Okay? So you're conflating the two different concepts. Or analysis of sequentially designed experiments. Some confidence intervals based on p-value ordering will exclude the actual sample mean that was observed. And this is a shameless plug for a paper that's based on my dissertation, where I showed that. So what p-values are not? They're not measures of evidence. They attempt to make inference via contradiction. In some sense, people will say, okay, the data are inconsistent with our assumptions and so on, therefore something else must be the case, which may well be, but it's not necessarily that they don't necessarily have to tell you what the something else is. P-values are not measures of reproducibility, despite the fact that they have a frequentist interpretation. And in fact, I think, as Jeff said, emphasis on significant p-values leads to lack of reproducibility, because a lot of these are just random significant p-values, random small p-values. And then the next time somebody tries to replicate it, there's regression to the mean. P-values are woefully incomplete. They are a measure of compatibility or incompatibility of data with certain hypotheses and assumptions that underlie the data collection, the model that was used, and so on, but it doesn't tell us what's more compatible. I think we need to always ensure that we provide estimates, such as maximum likelihood estimates, with measures of uncertainty. And many journals request estimates with uncertainty, but the editing is not consistent in terms of that. And so it's really up to us as statisticians to be more vigilant and insistent. This journal, Basic and Applied Social Psychology, provoked, I think, the current discussion because they said they would no longer require inferential statistics that are based on hypothesis testing, null hypothesis significance testing. And so I actually contacted the editor back in 2015, and I asked him, at that time they had just instituted, for some examples of what these papers would look like. And so it was still early in the process, but there were some that had come out that he agreed presented what that would look like. And so here's a paper about competition breeds desire, which was a kind of interesting study of people, whether or not you're competing for something, whether or not that makes that something feel more desirable than if you're just, in a classroom or something and instead of getting an award, the best test result is going to get a laptop. then that laptop is really, really a great laptop as opposed to just whatever. Anyway, the point is that here all they show are the estimates, so a mean, a standard deviation, and some difference measure, and that's it. So I don't think there's really that much that's lost, personally. So there are alternatives to p-values. One would be to, if in fact the way many people, I think, misinterpret p-values as the probability that the null hypothesis is true given the data. Well, that's not what it is. To do that, you have to apply Bayes' rule. And if you're going to use Bayes' rule, then you're going to have to, I think, be Bayesian, which is what we should do anyway. By the way, that shameless plug was my advisor, Butch Ciata, says that work is what drove me to become Bayesian. And then Bayes factors are actually a measure of evidence in favor of one hypothesis over others. And the p-value itself is not a good measure of evidence, as shown in this paper by Jim Berger and Tom Selke back in 1987, because they can show that using a Jeffreys type non-informative prior, the probability that the null hypothesis is true given the data changes as the sample size changes, which it's not supposed to do in the Neyman-Pearson sense. But in fact, the higher the sample size, the greater the probability of the null hypothesis. Even in this, and this is in the situation where you have a t-statistic that's right on the border. Multiplicity, as I said at the very beginning, I think the worst example of too many hypothesis tests are the situations where the data come to us pre-processed, pre-digested, and questions are asked of the data based on what the investigator may have seen. And we need to know what was left out. How did the initial analyses influence the research question? And how can we somehow adjust for that? Or at least we have to be sure that we are transparent about it. So conclusions. Medical journals perpetuate a reliance on p-values, I believe. And we should work to improve editorial policies of journals in our collaborative areas with respect to statistical inference. We have to focus more on presenting the data and placing the data in the broader context. As Jeff was saying, we can't treat each study as though it's the only study that's ever been carried out in a particular area. Again, if you're going to incorporate other information, I mean, you can do it in an informal way, or you can do it in a formal, coherent, probabilistic way through Bayesian inference. There has to be greater emphasis on replication and reproducing results, as we know, and many statisticians have said that journals don't tend to want to publish a study that sought to reproduce an earlier result, but they should. Educate our collaborators with respect to inference and alternative methods for assessing evidence, and then limit pre-processing and investigators' analyses. And one of the things that we're trying to do over in the Cancer Center is when somebody comes in and says we wanted to do a retrospective analysis or something, write a protocol. What questions do you want to ask? And specify, what the endpoints are, and we can talk about how we're going to analyze the data. Do all that before you put together the data set. Thank you.
Our next speaker will be Dr. Sklo. Use of p-values in reports of epidemiology studies, reasons for concern.
So where's my talk? Where? Here? Oops, one click. So, slideshow, okay. Thank you. So do I use this one or this one to move forward and backward? This one, this one, this one. Okay, good afternoon, everybody. I think I may be the only epidemiologist in this crowd. Am I not? Two, okay, that's great. So, my disclaimer is I'm not a statistician, I'm an epidemiologist. So I took a few statistics courses back in 1971. It's a Freudian slip. With Helen Ivey and Helen Kimball. Unfortunately, Meridian OS had not been born then, so Anyhow. So my concern as the editor for the American Journal of Epidemiology is really the misuse and misinterpretation, actually, of both p-values and confidence intervals. So the three epidemiology journals in their instructions for authors, they all seem to emphasize the idea that precision is more important than testing. So the International Journal said, we ask authors to provide the fact estimates with confidence intervals and exact p-values, and refrain from the use of the term significant. In other words, also discussion section. Epidemiology, actually, since immemorial times, does not want a report of p-values. They really want precision language. And they make an exception in tests for trend and in tests for interaction. Some specific testing, but in general, they don't like it. Now, the American Journal of Epidemiology said confidence intervals should be reported instead of p-values for estimated parameters. P-values should be reported only for relevant tests. And again, those relevant tests will be linear trend tests, heterogeneity tests, and so on. So what are the main problems in papers published in general, in epidemiology journals? And the fact that both p-values and confidence intervals can be misused. So I'm going to tell you a few things that you probably already know. One is the confounding phenomenon, to use significance to determine confounding. It's a bad idea. For example, a confounder may be ruled out in a case control study because there's no statistically significant difference in the level of the potential confounder between cases and controls. Bad idea. For example, a good example is age and menopause. There's a very, very striking relationship between age and menopause. And between the ages of maybe 44, 45 and 54, 55, the increase in percent menopausal is absolutely gigantic. Now, if you use this graph and you do a case control study in which cases are 52 years old and controls are 51, the odds ratio is going to be 1.7, which is not negligible, even though the age difference is negligible. And if the difference is 2 years, the odds ratio is 2.4. Has nothing to do with significance, right? So the question is not the difference is significant. The question is whether the difference, large or small, can explain, at least partly, the observed associations. Now, epidemiologists and epidemiology students, sometimes they get really nervous when the p-value is not given, okay? And they may even develop a p-value withdrawal syndrome with tachycardia, sweating, and some even die. So, of course, there's an emergency therapy if they want to focus on the p-value, and that's use a very high p-value as the cutoff point, like 0.20, 0.25. But in general, there's no relationship between p-values and confounding. Now, even the confidence interval is misinterpreted often. And this is an example of a paper which was published in the New England Journal of Medicine a few years ago. And you all know, when I have a paper published in the New England, I send flowers to my wife, I take her to dinner, and so on. So I didn't want to identify the authors, but this is lifted from the paper. It says this is a relationship between smoking and mortality from different causes. It says smoking was most strongly associated with mortality due to lung cancer, significantly associated with mortality due to cardiopulmonary disease, but not associated with mortality from other causes. And they say that because they misinterpret the confidence intervals as a flat function. The likelihood of the confidence interval is not a flat function. So most of the values inside the confidence interval are consistent with an association. So this is another thing. But there is another mistake that is so incredibly common. And it has to use the overlap in confidence intervals to state that there is no significant heterogeneity. So here, for example, there's an overlap, and you may assume the heterogeneity is not statistically significant, when in fact, this is a very conservative test, because you need a lot of standard errors in between in order for the test to be significant, if you use the overlapping rule. Okay, let's go back to the American Journal of Epidemiology. In the instructions for authors, they say, please refer to this statement from the American Statistical Association. I love this statement. I think it's great. And it goes on, good statistical practice as an essential component of good scientific practice emphasizes principles of good study design and conduct that Jeff Leake also mentioned, a variety of numeric and graphical summaries, and so on. And I like this. No single index should substitute for scientific reasoning. And it's interesting, if I go back to the epidemiology instructions for authors, they say that we are more open to testing with respect to modeling decisions, such as for test of interaction. So what I'm going to show you is what I think is important when I'm looking at interaction. And if I'm wrong, because I'm not a statistician, please set me straight, okay? So, evaluation of interaction in epidemiological study. All right, you start with, is heterogeneity present? No. Yes. If it is present, is it due to confounding? Yes. Trash? No. Is it due to bias? Yes. Trash? No. Now we got to the p-value. Is it statistically significant? All right. Yes. Is it a study with a large sample size? Yes. Now we have a problem. Okay, we are living in an era of multi-center studies, and therefore, probably should be ignored if heterogeneity is small for translational purposes. For example, if you're trying to identify a high-risk group, a group that shouldn't be exposed to an environmental risk factor, for example, but particularly in the absence of a strong biological plausibility and also an a priori hypothesis. So what about if it is not statistically significant? Well, is it a study with small sample size? Yes. Should be considered if heterogeneity is large. There is a strong biological plausibility or an a priori hypothesis, and a larger study should be recommended. So clearly, p-values and also confidence intervals are just one piece in the equation. I think it's terribly important to think about particularly biological plausibility. And 5 minutes, well, I think I'm speaking too fastly because I only have 2 slides to show. I should have timed it better. Anyhow, this is a study done by our own Ron Gray, so I'm going to speak more slowly so I can see if I can fill the 5 minutes. And this study is really interesting. It's one of the few instances when smoking seems to do good. So people who smoke, delayed conception is less, the odds is lower than for people who don't smoke. And you have confidence intervals for both estimates of the odds ratio. This is what the authors say. An interaction between caffeine and smoking is also biologically plausible. Several studies have shown that smoking significantly increased the rate of caffeine metabolism. And the accelerated caffeine clearance in smokers may explain why we fail to observe an effect of high caffeine consumption or fecundability among women who smoke. They take the 0.62 odds ratio as being null because of the very broad, very wide confidence limits. So do we need a p-value here? I don't think so. I mean, this is such a strong biological plausibility finding, plausible finding, that really even the confidence interval would be a little, whatever it is, whatever they are, I would pay a lot of attention to this finding. Okay, so what is the bottom line? Biological or sociological, psychological, etc., plausibility in an a priori hypothesis in an epidemiological study are more important, certainly, than significance testing. Probably also precision, but the last one is highly debatable. Thank you very much.
Our last speaker is Dr. Ron Wasserstein, and the title of his talk, Doctor, It Hurts When I Pee.
So I'm really grateful for the opportunity to be here. As Jamie said, I'm Ron Wasserstein, and my purpose in life is to illustrate regression to the mean. So if you're a parent, then you know what the talk is. 2 years ago, my wife and I proudly brought home 2 10-year-old boys from Haiti, and a couple of months after they joined the family, I was relaxing, watching a Nats game on TV, and my wife brought them down with a certain glee in her eye and said it was time for the talk. And that's challenging enough, but it's especially challenging when you're talking to a couple of boys who are just learning English. Well, a little while later, as we were thinking about p-values, it occurred to me that explaining p-values, especially to non-statisticians, is a bit like having the talk. They think they know all about it already because they've learned about it from their peers. And then it turns out to be not nearly as interesting as they thought it would be. They've stopped listening before you've stopped talking. And at the end of the day, chances are they now understand it even less than when you started. So why did the ASA issue a statement on p-values and statistical significance? Well, as I will soon illustrate, this is the problems that we've been addressing here at this panel are not new problems. They're things that have been in the literature forever. But it's a problem that was getting worse. And there's already been reference to the journal banning p-values. But we were seeing articles like this in Science magazine that was essentially throwing a whole lot of weight onto statistics for failures in science. That seemed to be very troubling, that was the tack that people were taking. And this same author in this same publication viewed the p-value ban as a giant leap for science. The ASA just decided it was time to weigh in that regard. So I only have a few minutes, and I'm not going to spend a whole bunch of time on the statement itself, but it articulates 6 principles, and I will mostly focus on the third one, with some scientific conclusions and business or policy decisions should not be based only on whether a p-value passes a specific threshold. Gary, I'll just say what Gary said with regards to principles 4 and 5. Okay, that proper inference requires full reporting and transparency, and a p-value or statistical significance does not measure the size of an effect or the importance of a result. Now, we wrote in the statement, let's be clear, nothing in the ASA statement is new. Statisticians and others have been sounding the alarm about these matters for decades to little avail. And when Nicole and I penned those words, we wrote them, but they were really the anthem for the whole discussion about p-values that took place with a couple of dozen experts in the field, because this was the realization that the problem's been around for a long time, but the problems are persistent. They just don't go away. And the statement seems to resonate because it's been downloaded about 150,000 times at this point, which for statistics, that's pretty good. For Shake It Off, which was downloaded 1.5 billion times at least, it's not much of a comparison. And John Oliver's reproducibility piece was downloaded 5 million times the first week. Okay, so it's all relative, but for statistics, that's pretty good. But this is interesting. Like I said, it's nothing new. Here's a quote. It's been widely felt, probably for 30 years or more, that significance tests are overemphasized and often misused, and that more evidence should be put on estimation and prediction. And who said that? Well, none other than the estimable D.R. Cox, and he said it 30 years ago. Okay, so that's a 60-year span at very least. Now, there's a rich world of quotes on the long history of concern about this that you can find at a website that David Parkhurst put together. The biggest takeaway message from the ASA's statement, in my opinion, is that bright line thinking, p less than 0.05, p not less than 0.05, is bad for science. And here's a quote from Ken Rothman. Scientists have embraced and even avidly pursued meaningless differences solely because they are statistically significant, and have ignored important effects because they failed to pass the screen of statistical significance. Ken says it is a safe bet that people have suffered or died because scientists and editors, regulators, journalists, and others have used significance tests to interpret results and have consequently failed to identify the most beneficial causes of action. Them's fighting words. So there's a wonderful website, I'll give you the reference in a minute, but it addresses, now what you're about to see are actual quotes from actually published articles that had a result where p-value was equal to or nearly equal to 0.06, okay? These are all publishable or published things. So this one said it was almost significant, almost attained significance, almost significant tendency, almost became significant, almost but not quite significant, almost statistically significant, almost reached statistical significance, just barely below the level of significance, just beyond significance. And this one, surely God loves the 0.06 nearly as much as the 0.05. And those two authors went on to say, can there be any doubt that God views the strength of evidence for or against a hypothesis as a fairly continuous function of the magnitude of p? Now suppose you got a p-value that was a little bit higher. Here are some things that have shown up in the literature. A certain trend toward significance, a definite trend, a slight tendency toward significance, a strong trend toward significance, a trend close to significance, an expected trend, the best kind, approached our criteria of significance, approaching borderline significance, which honestly sounds like a condition rather than something else, approaching, although not reaching, significance. Now, worst case scenario, the very worst case scenario is that you get a p-value that's close to 0.05, but not less than this, because this requires extra contortion skills. Hovered at nearly a significant level. Hovers on the brink of significance, just about significant, just above the margin of significance, just at conventional level of significance, just barely statistically significant. Here we go with conditions again, just borderline significant, just escaped significance, and just failed significance. And you can go to Matthew Hankins' website for these quotes, and unfortunately, hundreds of others. He said it was cited 3 million, or would be cited 3 million times, right? So Gary alluded to this fundamental problem that the p-value is not conditioned on what we would like to condition on most of the time. We often want the probability of the hypothesis given the data, but p-values give us something else. And this was illustrated in a lovely way by Ron Carver nearly 40 years ago. He says, what is the probability of obtaining a dead person given that the person was hanged? That is the probability of D given H. Obviously, it will be high, he says, perhaps 0.97 or higher. And so let's reverse the question. What's the probability that the person has been hanged given that the person is dead? The probability of H given D. Well, this time the probability is really low, 0.01, or really probably much lower than that. And he says no one would be likely to make the mistake of substituting the first estimate, 0.97, for the second one, 0.01, that is to accept 0.97 as the probability that a person has been hanged given that the person is dead. But he says, Carver says, even though this seems like an unlikely mistake, it's exactly the kind of mistake that is made with the interpretation of statistical significance testing. The thing is that inference is hard work. And one way that's been commonly used to make it easier while giving the appearance of objectivity is to set thresholds to make something statistically significant. And it's, I say appearance of objectivity because, as the other speakers have lined out, there are so many decisions that have gone into behind the scenes that so-called objective p-value that you often don't know about. So if we could change all that, we'd really like to. And in a world, let's imagine a world where p less than 0.05 carried no meaning, what would you have to do to get your paper published, your research grant funded, your drug approved, your policy or business recommendation accepted? I argue that you'd have to be convincing. You'd make good arguments for your position based on the nature and design of your study, based on what you knew going into the study, based on all the statistical results you had on hand, not just the p-value. And I think researchers really want to do that and know how to do that, but we have a culture of science that's been alluded to by the other speakers that has accepted the p-value as a filter for whether something can be published or not. And in a post-p less than 0.05 world, as I like to call it, this wouldn't happen either. The file drawer effect, where we put the non-significant results. Suppose you tested 100 null hypotheses that you knew to be true, okay? And on average, you'd have 5 of them be rejected with a type 1 error rate of 5%. And so you put the 95 not rejected into this file drawer, and you publish the other 5, and now you have a 100% error rate. So several people have suggested that the ASA statement didn't go far enough. They've said to me that we kind of left them hanging. And one concern that p-value experts had was that people would just try a straight substitution. Instead, okay, p-values, ASA says p-values are bad, which we did not, and 0.05 is bad. And so we'll just do this. We'll say, okay, if my Bayes factor is bigger than 6.87, bingo. Well, that's exactly the sort of thing that we don't want to happen, because we don't think fundamentally that there is a single index, one number, that is going to be truly usable as the only way to make an inference. So the ASA statement didn't go as far as it should go in many respects, but arguably it went as far as it could go in terms of where we are right now at the level of agreement about maybe what should happen next. So my 12 minutes are up, and I want to thank Brad Carlin at the University of Minnesota for the idea for the title of this talk. Thank you.
Thank you to all of our panelists. Before we start our question and answers session, I'd just like to draw your attention to some inserts in our program. There's one about a sign up for our community listserv and also for our work groups if you are interested. And the second, which is probably no surprise, is a short survey on our program today. You can leave these at the registration desk as you leave. Thank you. And we have 2 microphones that are mobile for questions. Thank you.
Have any questions for this panelist? Generate more discussion.
Thank you for organizing this session. Really wonderful talks. I just wanted to mention Professor Richard Royal wrote a monograph on statistical evidence, a likelihood paradigm. And I think that went into real in-depth about these foundational issues regarding how, as statisticians, we measure evidence, because that's one of the fundamental things that we try to do every day. And he's trying to point out the complexities or the challenges of measuring evidence and pointing out that p-values have a lot of problems and proposing alternatives, sort of like what Gary's talking about and Steve Goodman's papers about statistical evidence. But my comment is, in his book, he gives one example. I think it was alluded to by maybe Gary or so that Bayesians know very well that p-value is a strong function of sample size. So if you have two studies that are identically designed, except for the fact that one study is a much larger study than the other, but you get the same p-value from both studies, which study provides greater evidence? And both are significant at 0.05 level, right? Let's say the p-value is 0.01. Is a smaller study giving you a stronger evidence, or is a larger study giving you stronger evidence? So Jerome Cornfield wrote about this. He called it alpha postulate. I think Fisher also talked about it, where he says the p-value alone is the measure. The sample size doesn't matter. If you get the same p-value, then both studies are giving you the same evidence. But Bayesians would say that, well, a larger study, I can even detect much smaller effect size with the same p-value. So I just wanted Gary or others to comment on. I think this points out the fundamental problem with p-value as a strength of evidence. So how else would we use p-value, if not as a measure of evidence?
I'll go first. Is this on? Yeah, I guess so. That means you could hear everything we were whispering. Oh, my God. So I don't think you should use p-values for anything except if you're particularly interested in asking the question, given the assumptions underlying my model, given what I know about the study design, and assuming a particular hypothesis, how likely is it to have observed what I did observe or something more extreme? Because that's really all it tells you. I don't think that really provides a measure of evidence at all in favor or for what's really going on. I think our role is really to try to learn what's going on. And the example you gave, let's say, is so they had the same p-value, which means that they had the same standardized test statistic under the null hypothesis. But surely the larger one is going to have a more precise estimate. Now, they could have different estimates and still have the same p-value. So,
But it'll be a smaller effect, right? The larger one will have a smaller effect, and the smaller one will have a larger effect.
well, unless the heterogeneity is different too.
Right, so that goes to your comment. You made a comment, Moses, about if the effect size was larger, even though the sample size is smaller, then you should put more, you should look into it more closely. And I think that would always be the case. A smaller study, if it gives a significant p-value, then the effect is likely to be larger.
Now, what I said is that if it's biologically plausible, if you have an a priori hypothesis, and you just missed getting to one of those almost significant, then you have to pay attention to it. That's what I said. Even if this, the sample size can be small, but the results are exactly as expected given the plausibility of the hypothesis. I think that's terribly important. And I think one of the problems in epidemiology these days, exploratory studies are okay if you don't know anything about the condition. But I think you have to be careful about it. I think studies that have a priori hypotheses are much stronger because then you can be a little bit more sure of the plausibility of your finding.
So great talk. I was wondering, what are your thoughts on, I think some of these issues can be potentially solved with like registration of hypotheses and that kind of things, because doing consulting work here and in the past, I've seen people come and say, I have all these variables, I have no idea what anything's related to anything, but this is my outcome, go. And I've seen that, it's not uncommon to be heard, but like there's, I don't know about places to like register them or something like that to make it more of like a priori actually hypothesis. Even though a lot of papers state they're a priori, I'm very skeptical on a lot of those. So what do you think is a good way? Because otherwise I see the potential to say, we don't have necessarily that great of a question, we've collected this data and we want to publish a paper, and that's not a great way to do science in my opinion, but that is the way science is being done around science all over.
I would just point out that there's very easy ways to do pre-registration now. There's a website put up by Uri Simonson at Pennsylvania, and the Open Science Foundation also has a pre-registration website. and you basically just upload information about your hypothesis and then run your analysis. Now, it's not holding you to it in any sense. There's also several journals that now take pre-registered, will peer review your paper on the basis of the study plan and then decide acceptance or rejected before you analyze the data. And so there are opportunities to do that. I think, sometimes the thing, like penicillin wouldn't have been discovered if we only did pre-registered hypothesis testing. So that's kind of a knock against only pre-registering things all the time. But I do think that there's ways to do it to some extent now, that are easier than used to be.
Can I make up, I'm sorry.
No, go ahead.
A related point, another problem with the p-value is that if the results are not significant, many people would not submit the paper for publication. So I think publication bias and the significance is a major criteria, has been shown in many studies, including by Kay Dickerson in the EPI department, to be a criterion to either publish or not publish the paper, which I think is terrible, right? I mean, it distorts the situation. I mean, if you're talking about something that can be translated into a policy or some action.
I just wanted to add or repeat something I said. I mean, in the world of clinical trials, people write protocols. The protocols get reviewed. And part of the protocol is to write down the analysis plan with respect to the primary and secondary endpoints and so on. Why not do the same thing for other kinds of studies, observational studies, retrospective studies? And so we try to do that with, I have to admit, not complete success, but we're trying to institute that, where we sit down and we discuss with the investigators, what is it that you want to, what questions do you want to answer? And how can we best do that without doing a lot of data dredging and so on? And in much the same way that we would sit down with any investigator doing a prospective randomized clinical trial or some other prospective study where they had to write a protocol, say, because it was going to get reviewed, peer reviewed. So, I mean, we try to do the same thing. And I think whether it's registered somewhere or not, it's, I think, less important than having the statistician and the investigators working as a team on the project and carefully designing the study, including prospectively deciding on the primary endpoints and ways of analyzing the data.
So may I offer sort of my personal experience? So I usually will sort of ask the client who his or her senior faculty mentor is.
So far, so good.
What if they're a student and this is their proposal and
Yeah, I usually ask whether there's a senior person that's guiding him or her on the project. And then we usually will arrange a sit down all together and then talk about the science and then come up with some research questions. My personal experience in terms of consultation is that they usually lead to a more happier, more satisfying experience.
and if the results aren't what they expected, it ends and you publish? Because I haven't, that is not my experience. If that is the outcome, and then the project continues with or without me, down the road I might not travel now.
Okay.
Actually, in Kay Dickerson studies, often the papers are based on studies that had been finished, had terminated. They were not published because the authors didn't think the results were interesting, which I think is silly. What's interesting is the hypothesis. If it is a good study, it has to be published with or without positive results.
Congratulations for presentations. My question for Dr. Westerton. After the statement was published, the journals changed something? You feel that some? Because personally, I have a lot of problem with when you not show the p-value, the review editor, or you have to show the p-value of something. Do you see something change after the statement was published?
We're about 6 months out from publishing that statement, and I've gotten some communications from a small number of journals that have indicated that they're making their authors aware of the statement, and they're putting more focus on thinking those issues through for their journals. We expect that, we expect a change over time and not tons of time. Didn't expect it to happen in 6 months. However, that paper, the p-value statement is being heavily cited in non-statistics journals, which I haven't had the time to go through all those papers and see if they're just citing it and then going ahead and doing whatever they did before anyway. But at least there's some attention being paid to it.
I mean, do the journal editors contact you?
A few have. But we haven't done a really good job yet of telling them what they should do instead. So I think there's a lot of work to be done in that regard.
Just to follow up on that.
If we're trying to get emphasis away from regarding 0.05 as a binary decision point, how do we incorporate that into power calculations, or should we do away with power calculations?
I think,
Especially because we need them when we write grants.
yeah, so I think this brings up an important point that Ron brings up, which I agree with, all of the criticisms of p-values hold, right? But the p-values, what are you going to replace it with, and what are the problems with that approach? And we'll discover them all as we go. So like, imagine Ron came out next week and said, everybody has to do confidence intervals, or everybody has to do, pick any procedure you make everybody do. People will figure out how to game it and cause problems with it and cheat with it and all that kind of stuff. Like the pressure is still going to be there tomorrow to get grants, right? And that's not going to disappear because we don't use p-values anymore, and it'll be just a new thing that we're gaming, and then everybody will hate the new thing. So I think that the broader issue is that, and I think Ron pointed this out very nicely in his talk, was that statistics is getting blamed for a cultural problem in science. Like we're pointing out the p-value is the problem, but it's a cultural problem brought on by the fact that we don't have enough money for everybody to do whatever they want in science, right? So I don't know if there should be power calculations or not, but I think it's silly that as an editor I also edit a journal, and as an editor of a journal, I think it's ridiculous that you would just ban inference entirely and ban p-values entirely. First of all, because I'm a statistician, but second of all, because what are you going to replace it with? That example that was shown where there's standard deviations and means and everything. How do I interpret whether there's something real going on? Do I have to know their area, the exact type of data they've measured? What's a reasonable effect size in their area? And they can explain it to me, but do I believe them? They're trying to game me. I'm the editor, right? Like they're trying to get past me. So I think that there's this focus on the p-value at the exception of the fact that there's a behavioral issue that has to be solved, a cultural, behavioral, societal issue that we have to solve. And it's kind of easy to point to a p-value and say it's a stupid number, but any other number would be stupid too.
And I think a lot of it goes to what you said about statistics being an afterthought, because really the power calculation shouldn't be, the investigator comes to you and says, tell me what I need to get p equals 0.05, but you really sit down and talk about what's a meaningful difference,
Right.
What levels of precision you have, all the things that should go into it.
Yeah.
So I've got a quick follow-up question. So, another area where we see this same issue of this, idealizing reaching p equals 0.05 is in meta-analysis, because we say, oh, we've got a bunch of studies where we don't have p equals 0.05, but there's a trend, and let's put them all together and we'll get p less than 0.05. And these get published all the time, and I do meta-analyses, so I don't have a problem with them, but what they should be doing is looking for what are the reasons for heterogeneity among the studies, has confounding been controlled or bias ruled out similarly in the studies, and not just if you put a whole bunch of p's greater than 0.05 together, you'll get less than 0.05.
So if I could comment on that just a bit further, one slide that I wish you would, that I think Jeff had, that I wish you would impress in your brains is the one that showed all the steps before we got to the p-value, and then the fact that all of the focus becomes the p-value without thinking about how any of those other things got us to that point. And in a longer version of this presentation, I have a study from a journal of sleep science. It's not the name of it, but that's the right area, where they do a tremendous job in this paper of laying out really everything that they did and every choice that they made and every categories that they combine, and they really do a tremendous job of being transparent and saying, you know, these are the decisions we made that led to the results that we got. And then at the end, all of the conclusions and all of the thinking about what's been learned from that science is based on what the p-values came out to be. So it's like, on the one hand, there seems to be this recognition that all these things led to a p-value, but no recognition about, well, what might have happened if we'd made a small change here, if we hadn't combined those categories, if we hadn't done those things. And so they can be really transparent and still, at the end, do just exactly what Jeff's slide showed, just completely focus on the p-value.
Let me just add something to Bruce's first question about power. Power is a different thing because it's before you've done the study. And so p-values are after you've analyzed the data. So there's a distinction there. I'm not saying, I mean, power does have, there are other issues that I have with power, with the reliance on power. But ultimately, what you need to do is you need to figure out how precisely you want an estimate. And that's really what it's a surrogate for. It's a surrogate for figuring out how precise your estimate is going to be.
So, in terms of power, could I add that my personal experience is that because the IRB requires power sample size, so every investigator knows that they have to do power calculation. But then not all of them, and then quite a few of them don't even know that you need two specific hypotheses to do power calculation. And I think so in terms of requiring to think about those kind of things and get them an opportunity to talk with, or forced to talk with a statistician. And I view consultation as an educational opportunity, even though it may not be a very efficient way. So I really sort of echoed Jeff's slide in terms of the 4-year medical school education. It's the no exposure to proper scientific methods in terms of qualitatively, handling the data, answering questions. So I think there's some fundamental things that need to be considered.
So on Jeff's slide, you had a slide that you do certain things because someone told you to do it that way. So the departments of biostatistics and epidemiology educate literally every student at Bloomberg in one way or another. So how would you suggest we incorporate the things that you presented today in the education of MPH students, master's students, and even doctoral students?
I guess anybody can answer, but it's my slide, so I'll say first. I'll talk first. I think that there's two components to that. One is I think that to the extent that I'm aware, I'm like not involved in the like major teaching efforts to the people here at Hopkins, but to the extent that I'm aware of it, I think they do do a really good job of describing the best practices of what we, I think it's like, we don't teach every medical student, for example. We do teach all the MPH students and so forth, but I think that it's more a matter of distribution as opposed to whether we're teaching the right things or the wrong things, so to speak. I do think that in my area, at least, genomics, where I can speak, somewhat intelligently, I would say that the problem is not that we're not teaching people stuff, it's that often we don't know the right thing to do. There's no evidence to suggest it's better to correct with Benjamini-Hochberg or Q-values for multiple testing in genomics data set. Like, there's no body of evidence that should suggest one of those two things is better, and yet that's one of about 450 decisions I have to make in every data analysis I do, none of which there's any evidence to suggest this way is better than that way, with a few very narrow exceptions. So I think, at least for me, I think the first step is collecting information on what's the right thing to do, and I think that's we haven't solved that problem yet, and it's something that, as a field, we've focused on the mathematical optimality of methods, but not the empirical optimality of which methods work when you put them in the hands of users. And so that's something that I think maybe we should do some research on.
So, as the only other epidemiologist in the room, I have the impression that I probably work with more observational data than most statisticians, although I'm sure that you've all worked with observational data. I wonder if the panelists could comment. You did an excellent job, I thought, pointing out all the decisions that go into the analysis that are going to influence your p-value, but there were what I found in observational research is that the bias is often much stronger than, has potential to be much stronger than even any signal. And given the p-value comes out of this statistical theory where there was some sort of randomization that just doesn't exist. I mean, can you speak at all to some of those distinctions, and is there even a stronger case against reporting p-values when you're in an observational setting?
I don't know how to answer that question. If it is, the p-value, I think the p-value is limited in general, but I'm not sure it's more limited in observation and in randomized clinical trials. I really don't know.
Well, in terms of the mathematical foundation, the
It
mathematical
is, yeah,
foundation
sure,
is
of
based on
course.
randomization. But yeah, I mean, if it's a randomized trial, you can feel a little bit more secure about controlling bias, but you're absolutely right. You can never totally rule it out, even in a randomized trial. But observational studies, you're on even shakier ground, and you just have to acknowledge how the patients or how the individuals who participated or whose data you're analyzing, how were they collected? You know, who got in, who didn't get in, all those things, and you have to leave it up to the reader to decide how much weight she or he wants to put in what you're presenting.
I wonder if we should be putting more emphasis on, this doesn't work, on supplementary analyses or sensitivity analyses to try to make our point as opposed to, one estimate.
But I think even for randomized trial, we need to think hard, right? For example, a simple example is that once you have missing data, a randomized trial data become an observational study, right? And you have all kinds of confounding and all those issues you have to face, you have to think hard. Not because you have a randomized trial, then you're home free.
Anybody else want to add to the discussion?
So I'm wondering if there's much discussion about the distinction in interpretation of p-values in the sort of classical manner versus attained significance levels. And the reason I ask for that is because if you think of p-values as attained significance levels, then any criticism of p-value is really just criticizing hypothesis testing in general, not specific to p-values. They're just a convenient way to report the outcome of a hypothesis test.
I agree that it's all, okay, so hypothesis testing as opposed to estimation. Answering the question before about education, I think there needs to be more emphasis on estimation and maybe a little bit less on hypothesis testing. And then I also agree that hypothesis testing in and of itself is going to be fraught with problems. Those problems, though, are exacerbated by setting these bright lines, as Ron said. And so that's what we need to try to get away from. I mean, if you want to view it as a decision process, that's one thing, but we don't do it that way. In fact, we tend to use, or at least articles that I read in medical journals tend to consider p-values as an estimation thing as opposed to a decision.
So Brian, I will just tell you that one of the people who worked on the discussion about the p-value statement very strongly viewed p-values as a descriptive statistic.
You mean contrary to thinking of it as attained significance levels?
Right.
Okay.
We're out of time now, since it's 1:30. I just wanted to say thank you again to all of our panelists and for attending our event today.